Okay, today for your warm-up, you're asked first for the first 6 problems to go ahead and find exact values of x and y for these special right triangles. I've already got the answers written here for all of you, so what I want you to do is start by pausing the video, work through those problems, and then you can check your answers and then start the video back up again. For problems 7 through 10, converting each angle from radians to degrees. I'll do number 7 with you guys, and then I'm going to put the answers up here for the other 3. So just remember, Mr. Jolly said last time, we're going to take, if we're going from degrees to radians, we're going to multiply by pi over 180. And he said we do the pi over 180 because pi radians is the exact same amount as 180 degrees. Okay, so we end up getting something that looks like 135 pi over 180, and then we can go ahead and simplify that, and Mr. Jolly says you can do that with your calculator, use the simplify fraction button, and this should simplify down to 3 pi over 4. Okay, so that's what number 7 would look like. And remember, for numbers 9 and 10, you're just going to do the opposite instead. You're going to multiply by 180 over pi, and then those pi's should divide out when you're doing these types of problems. All right, so go ahead and pause the video now, work on your warm-up, finish these last 4 problems. Okay, hopefully you guys have finished up your warm-up. I've got all the answers here written down. I cleaned it up a little bit, so we just have the answers written. Again, this is just for you guys to practice. It's really important that we feel comfortable with these special right triangles and being able to solve them fairly quickly. We just need a lot of practice with that, so that's what we need to do the next few weeks here. All right, as well as converting from radians to degrees, also very important. So make sure you're comfortable with that practice today. Moving on, today's assignment, first thing we want to look at is just a circle in general, degree and radian measures of special angles. Okay. What we talked about last time was the initial side. So I'm going to mark the initial side here. This would be our initial side if we were going to be rotating counterclockwise and finding a terminal side angle. So that's where the initial side starts of a standard position angle. A lot of vocabulary from what we had last time. Now, if we were starting here and we didn't rotate anywhere, we would go a total of 0 degrees. Okay, we would also rotate a total of 0 radians. Now, if we rotated halfway around the circle, we would go 180 degrees. And Mr. Jolly talked about it last time. 180 degrees is the same as pi radians. So what we're going to be doing today is we're going to start by filling out this entire circle with all of the radian measures. So if we did a complete full circle, we would also be at 360 degrees, or we'd be at 2 pi radians. And a really good way to think about this circle is by breaking it into fractions of the circle. So for example, we started with one full circle was 360 degrees. Well, half of the circle rotation got us to 180 degrees here. That's where the 180 came from, half the circle rotation. Half the circle got us to pi radians. So now, what happens if we take that half and we only go a quarter way of the way around the circle, or, for example, we cut 180 in half? Well, that's going to make this 90 degrees. And what's half of 1 pi? It would be 1/2 pi. Or another way we write it is pi over 2 radians. And that's kind of the idea here. If we went 3/4 of the way around the circle, we would be at 270 degrees, or we would be at 3/2 pi, or 3 pi over 2 radians. And one thing that we can do with this circle is we can actually count by fractions. And what I mean by that is if we were going every half rotation around, we could keep rotating. We could go 1 pi, 2 pi. We'd go 1 pi halfway around. And then if we went a full circle, we'd go 2 pi. If we kept going, we'd go to 3 pi, and then 4 pi. etc., etc. That's going to keep happening the more we rotate around. Okay, that's something that I really want us to focus on there. Okay, but we could also count by halves. And what I mean by that is we go 1/2 pi, 2/2 pi. That just happens to simplify to pi. 3/2 pi, that's going to be 3 pi over 2. And then we go to 4 pi over 2. And 4 pi over 2 happens to simplify to 2 pi. So one way we could do these types of problems, figuring out what angles there are, is we literally just rotate all the way around the circle. Okay. The next thing we'll want to do is we'll want to think about what's half of 90 degrees. And that happens to be 45 degrees here. And we could count by 45s around the circle. We can say 45, 90, 135, 180 is the next one. And then we go 225, 270, 315, 360. So if we were counting by 45s around the circle, that's how we'd go. And we can do the same thing by counting with radian measures instead. So first we have to take pi over 2 and say, well, what's half of 1/2? Or don't worry about the pi right now, just think about this as a 1/2 fraction. Half of that would be 1/4. If we were to convert that to radians, it's just going to be pi over 4. We could write that instead of 1/4. But then we can count around the circle. 45 degrees is 1 pi over 4. 90 degrees is 2 pi over 4. 135 degrees is 3 pi over 4. 180 degrees is 4 pi over 4, and it simplifies to 1 pi. 225 is 5 pi over 4. 270 is 6 pi over 4, which simplifies to 3 pi over 2. 315, that's 7 pi over 4. And 360 is 8 pi over 4, which is 2 pi. The last two angles we're going to focus on here are going to be the 30-degree angle and the 60-degree angle. Okay, let's start with the 60-degree angles. The 60-degree angles are going to be represented by all of these blue lines here. Whenever we talk about 60-degree angles, we're always talking about the angle farther from the x-axis. If you're ever confused about that, the 30-degree angles, I'm going to highlight in red here. Those ones are much closer to the x-axis, those 30-degree angles. Let's start with the 60s. If I'm counting by 60 degrees, what I would need to do is I would start with pi over 3 radians. A good way to think about this is actually going back to the 30 degrees, because I've 90 is pi over 2 radians, and I would just say 1/2, and then I need 1/3 of that, which comes out to pi over 6 radians. And then 60 would technically be 2 pi over 6, which is pi over 3. But let's count by 60s first. I go 60, 120, 180, then I go to 240, and then I go to 300, and then finally 360. If I'm counting by radians, it's going to be 1 pi over 3. Then it's going to be 2 pi over 3 radians. 3 pi over 3 radians is pi. 4 pi over 3 radians is 240. 5 pi over 3 radians is 300 degrees. And then last but not least, the 30-degree angles. We have 1 pi over 6 at 30 degrees. 2 pi over 6 happens to be 60 degrees, which is pi over 3. 3 pi over 6 is 90 degrees. That simplifies to pi over 2. 4 pi over 6 simplifies to 2 pi over 3. That's 120 degrees. And then we have 5 pi over 6, which happens to be 150 degrees. 6 pi over 6, 7 pi over 6, that's 210 degrees. 8 pi over 6 is 4 pi over 3. 9 pi over 6 is 3 pi over 2. 10 pi over 6 is 5 pi over 3. And then we get to 11 pi over 6, and that just happens to be 330 degrees. It's a little tight here, but that's the idea with our angle measures here, are going around the entire circle using both radians and degrees. Okay, again, they're just different units of measurement, but they mean the exact same thing. Just like if we were talking about 1 meter is 3.28 feet. It's the exact same thing, it's just different units of measurement to measure it. All right, a little bit of new vocabulary here. We're going to look at this graphic down below, and we're going to be talking about sectors and central angles here first. The first definition is a sector, and that's defined as a region of a circle bounded by 2 radii and an arc of that circle. What I mean by that is right here we can see 2 radii right here, and that's going to be forming this sector. This arc of the circle is going to be helping form that sector as well. The second definition is the central angle, which is the angle formed by the 2 radii. And if we notice down here, the central angle does not need to be in standard position. It can be anywhere on the circle. That's really important to note, that a central angle is different than a standard position angle. Okay, so it is not a standard position angle. Very important to recognize that. Another thing with central angle is it is defined by the Greek letter theta. And with the Greek letter theta, that looks like almost like a zero or a circle with a slightly arced line through it. That's the way I would draw it by hand. Okay, and that's the Greek letter theta. That's going to represent any angle we're dealing with. So there are 2 equations that we need to know right here. We need to know the arc length of an equation. Okay, and the arc length is represented by this letter S. It's going to be lowercase s. The other thing we need to know is the area of the sector, which is represented by the letter A, capital A. So the formula for arc length is going to be represented by this letter S, and then it's just R times theta. The formula for area is represented by the capital letter A for area, and it's going to be 1/2 R squared theta. Now, if you're planning on taking the IB exam, don't worry, these formulas are given to you on the IB exam. They're both given to you, okay? But one thing that's really, really important about this, angle theta must be in radians to use this formula, or these formulas. That's where the circle up top comes in handy. Because if I say, hey, angle theta is 90 degrees, well, I can't find the arc length or area with these formulas. I need to say, oh, 90 degrees is the same thing as pi over 2 radians, and now I can plug in pi over 2 and solve for these formulas. Let's go ahead and take a look at a couple examples here. So first example is a softball field forms a sector with the dimensions shown. Find the length of the outfield fence and the area of the field. So it asks for the length of the fence. That's going to be arc length. And then the area of the field. That's going to be our sector area. Okay. So starting with the arc length, I see we have a 90-degree angle given to us right down here. So again, we just talked about that 90 degrees. That's the same thing as pi over 2 radians. We could also do 90 times pi over 180 to find that value. And if we do the 90 times pi over 180, we would simplify it to pi over 2. Again, we already know how to do that though, or we have our circle above. So we're just going to use the pi over 2 from that. To find the arc length, we're simply going to say, what's the radius? In this case, it's 180. And we're going to multiply that by pi over 2 radians. Simply to work on this math, 180 divided by 2 is 90. So the arc length comes out to 90 pi feet. Don't forget your units. Okay. Now, if I asked you, hey guys, go ahead and tell me what's the length of that fence there, and you came back and said, hey, Mr. Street, length of that fence is 90 pi feet. Well, that's your exact answer. Okay, that's good. Exact answer. But what the heck does 90 pi feet mean to me? So what we need to do is we need to approximate this answer as well. So we need to multiply 90 by pi, and we're going to come up with our approximate answer, which is approximately 283 feet. Okay, so there's a difference between our exact answer and our approximate answer. Sometimes if we don't have a calculator, we can find the exact answer and just leave it as 90 pi. If I need to find an approximate answer, just go ahead and put it in your calculator and then round to the nearest foot or tenth of a foot, whatever the problem's asking you to do. For the second part, looking for the area, and we're going to do 1/2 times our radius squared times our theta, which is pi over 2. Very important here, we got to follow our PEMDAS, order of operations. We have to square the 180 first. It's really tempting here to say, well, 180 times 1/2 is 90, and then we square 90, but you'll get the wrong answer every single time. Follow your order of operations when solving these problems. So this one actually simplifies out to 8100 pi, area is always feet squared, units squared. And then again, we just multiply 8100 times pi. This one comes out to something like 25,447 feet squared. Okay, so now there's one more example here. It's the Space Needle problem. Basically, we're just saying the top of the Space Needle in Seattle, Washington is a revolving circular restaurant. I give you the radius of the restaurant, happens to be 47.25 feet, and it completes one revolution in 1 hour. Okay, so it says about an hour. We're just going to assume it's an hour. So you have dinner at a window table from 7 p.m. to 8:55 p.m. So you have dinner for almost 2 hours. Okay, so how many feet do you revolve? We already know we're going at least one full revolution around, and then we have to think about how much of a revolution are we doing the second time. So one full revolution and then a certain amount of the second revolution. Okay, so go ahead and think about that problem. Pause the video right now, and I'm going to put the answers up and work and talk about this problem with you guys in a few minutes here. Okay, so there's a couple ways to think about this Seattle Space Needle problem. One way to think about it is we're revolving a full circle around, right? So that's going to be the first hour. And when we're doing one full revolution, we're going a full length around this circle, which is like the full perimeter of the circle, which is also the circumference. And if you guys might remember, this area for a circumference of a circle is 2 pi r. Okay, so 2 times pi times the radius. 2 pi, that happens to be your theta, right? Sector arc length, think about that up here. R times theta. Theta happens to be 2 pi radians, okay, times your radius. That's where the circumference equation comes from. Okay, the arc length is just a thing of working with that. So if we wanted to find one full revolution, we can just say 2 pi times 47.25. And it turns out that we've gone approximately 297 feet in one full revolution. Now, the second revolution, though, we haven't taken into account yet. So what I said over here is there's one full revolution and then 55/60ths of a revolution. Okay, I got 55/60ths because there's 60 minutes in an hour, and we're rotating for 55 of those 60 minutes. Okay, so that's one way we could look at this problem. So I could say, okay, well, the arc length then for the second revolution is going to be that same 2 pi times 47.25, except I want to take a fraction of the circle instead of doing 2 pi, which represents the full circle. I want to do times 55/60ths, and I end up getting something like 272 feet. So that means in 1 hour, if I add these two things together, I'm going to get 569 feet for my almost 2 hours of being in the restaurant. So that's 569 feet of rotation or revolution. All right. The other way I could do it is I create this fraction over here. Let me highlight it for you. This 1/15 60ths, because that's 115 minutes and there's 60 minutes in an hour. And I could technically use this arc length equation and say 2 pi times my radius 47.25 times 115 over 60. And again, multiply it all together, and I should get that same number, approximately 569 feet, rotated in that whole time. So 2 different ways to look at the exact same problem. Okay, for the last part here, part B, it says, do diners seated 5 feet away from windows revolve the same distance? So if you're seated 5 feet away from the window, are you going to be closer to the outside or closer to the inside of the circle? And the answer is going to be closer to the inside. We're sitting 5 feet away from that window. So that makes the radius 47.25 minus 5. Our radius is 42.25. And if there's a smaller radius, are we going to revolve faster or slower? Okay, or would we revolve farther or not as far? And the answer would be we revolve not as far. We do not revolve as far. All right. All right, so go ahead and take a look at your assignment now. Get that work done and go ahead and submit that assignment. Hopefully this video helps you out on that.